I hope my slides are visible, but recording has not recorded. Yeah, it has started. Okay, thank you. So today we'll have this new topic. In fact, this is the last topic of this subject for this semester, and that is on reinforcement learning. So the references are this. You can go through chapter 18. I think it is better explained in this chapter in Alpedin's book, but Tom Mitchell's book is also very good. There also chapter 13, and both of them deal with almost similar things. I mean, almost similar concepts they have discussed. Alpedin's is, I found, a little organized expressing the thing. And most of my, the slides, they are made from Alpedin's chapter. So let us try to understand this particular paradigm of.
final marks
Can you please unmute?
ML2 కి
Please mute.
అందులో నాకు 48 ఉన్నాయి మూడులోనేమో 50 ఉన్నాయి.
Someone's microphone is. I hope it is muted now. Okay, thanks. Still someone's microphone. I think Shai Shantoshi, please mute yourself. Okay, thanks. Right, so let us try to understand the paradigm of reinforcement learning. And in a very simple way, we can say that here the learning takes place with a critic. If I draw the analogy with respect to our human learning of concepts, how critics help in our learning process. So the role of a critic that we need to understand, and then how it is extended under this machine learning framework. So let us understand who is a critic. So as the first thing is that there is a difference between a teacher and a critic. Like teacher does not tell us what to do, but I mean the critic does not tell us what to do. Teacher, of course, teaches us what to do and how, etc. Various questions. So teacher can be also a critic, but a critic is a specialized role. Special role. It is an evaluator. It evaluates past performances, and it provides feedback to those performances. And this feedback may not be readily available always. It is scarce and it is given. So this is the kind of nature of an environment when you consider a learner is an agent, and it is interacting with an environment which is represented by a state of the environment in this abstract form. So the schematic diagram is just explaining the thing. So you see that agent is interacting with the environment. So interacting means acting. There is some action. Agent is taking some action. Which environment is also in some state S, right? Some state, and on that state, agent is taking an action. Then environment behaves. Environment rewards agent, may or may not. That R is that reward or penalty, whatever. It could be in the form of penalty or in the form of reward. We will consider these are all rewards, and the state may change also. So this is what it can. The action may change the state also. So it gets reward or penalty sometimes by that. So that is the role of the critic. So there is a critic. Environment has a critic, and who sometimes will give you reward. So from the agent's perspective, agent can sense the state of the environment and also can receive the reward if available. Of course, agent can take an action on environment. So there are certain options of actions, set of actions. Agent can choose certain actions. And the objective here, from the agent's perspective, is that why they're doing, it's like there is a certain goal state in the environment, agent tries to reach that. So out of those states, there is a favorable state, desired state, which the agent wants to be, wants that environment to be in that state, right? So So that is the motivation of acting. So agent takes an action so that it can reaches the goal, or it can brings the environment in that desired state. And then the reward is with respect to that only. How well, how far the agent is from reaching that goal. That is the kind of reward, whether the agent is successful or not, whether the agent fails to reach that state. So in that way, the rewards will be given to the agent for by a critic. So it learns a series of actions. So what is the learning in that case? So as you see that the agent has to learn a series of action by which it can reach a goal from some state, right? So in an arbitrary way, you can say that given environment in some state, agent has to learn a series of actions to reach that goal, or given any arbitrary state of environment, agent's learning would be such that it should go to that state by taking a series of actions. May not be single action is not possible. It has to be a series of actions. It is not that there is an action which will directly take you to that goal, depending upon the state of the environment. So in some state, it may be possible naturally when you are, it's a series of actions means there is a state on which, by acting on which you are reaching a goal. But there are states where immediately you are not able to reach a goal. So you think about any game, particularly chess is a good example. The chess board, the places of pieces, the arrangement of pieces, that gives you a state of the chess board, chess game. So an agent can take, a player can take certain moves, right? Of course, when you are playing a game, there is also an opponent there. So it has also another factor there. So we are not bringing all those things into this particular learning task. We are simply considering the environment is there, and environment will always give you a state. So which means there the opponent is like an environment, maybe an opponent. Environment might have some other objective also. So we are not considering those things. We are simply considering the response. So opponent's move is basically the state, right? So the idea here that it tries to maximize the total rewards from any state. This is in an abstract form. So rewards could be cumulative. Rewards could be just reaching the final state. So the way you can see, or rewards could be in a form how far agent could complete or can go near to the state. So I will start with a very simple example. It is called K-arm bandit example. So it is very simple in that sense that it has a system and which has only K levers. Okay, and the action here is that you have to pull a lever to win a reward. So a reward is associated with an action. So whenever you pull a lever, you can get some reward, right? And your task is that to decide which lever to pull to maximize the reward, right? So, I mean, it looks very obvious if I consider that at least in one go, you can pull one after another a lever and you can see what is the reward you are getting. And if these are very deterministic, and actually it is a deterministic framework right now, if I consider that, then after K trials, you have learned. And then you know that which lever is giving the maximum reward. In fact, that is a kind of reinforcement learning strategy that you have to explore. And then you find out which lever is giving the reward. So that is the difference. Like in supervised learning, already as if the supervisor will tell you that which lever leading to the maximum earning. No. While at reinforcement learning, this kind of exploration is required. And you have to keep track of the best, whatever you have received so far. So though it is simple, it has those flavor of these two different learning paradigms. And here, of course, the machine is in one state only. We are considering only in one state, and it is giving this reward. And only we are considering at that state, taking an action. So out of possible k levers means there are k possible actions, pulling a lever. So we are representing, for example, QA is a function of action. It's a value. We are considering a value. And initially, as you can see, we are putting all of them uniform, 0. And then you are getting a reward and you are storing them. So it's a kind of tabular search, finally, find out whichever is maximum from the table. Wherever you get the maximum, choose that action. So that is a simple learning framework. If I just make it a bit more complex in the sense that this is not a deterministic reward, you get reward non-deterministic way, which means there is a probability distribution associated with getting a reward given an action. So we can see that we cannot simply write a single value reward, associate a single value with the action. There is a probability distribution with that. So which means that once again, statistically speaking, you have to consider what is the expected reward, and you try to maximize that expected reward in that sense. So you have to learn that, right? Now this distribution may not be given to you. You have to learn this distribution also. So that is the complexity here of this reinforcement learning. So the task is to decide which lever to pull to maximize the. So the task remains the same, and learning objectives remains the same, to try different levers or methodology levers and keep track of the best. Now here, keep track of the best for expected average, right? So I'm sorry. So this is what we are representing now. We are considering for every the tabular. If I consider the tabular representation of my function q, here we have another factor that at time t, okay, because it is non-deterministic. But what we are doing, what is the expected reward so far at time t. Now this can be it is that for an average of all past rewards when A was chosen. This is the I should say definition of this QTA. So what kind of computations you can do here, which means now you are always keeping an average, and when you are getting an incremental reward, you are or reward, immediately you make an instantaneous update of this average. You can do it in various ways. Now, one of the interesting way to put it, and which has a very similar framework of previous learning updates rule. If you have noticed the similarity, that suppose this average of reward for action at time t is QTA, that is the definition, and you get, after taking that action at time t, you get a reward, which means that is now the t plus 1th time point reward at that point. So you update this running average, update the average by adding this factor. So you can see that we are simply updating by taking the difference, adding the fractional of the difference. Eta is a fraction, basically. It is in the range of 0 to 1. It's called learning factor. Actually, if I expand this term, you will find it is the weighted average between QTA and RT plus 1A. Weights are, for QTA, weights is 1 minus eta, and RT plus 1A, it is eta. So if you keep eta within 0 to 1, it is simply the unweighted average, right? It is simply unweighted average, and also this representation, that difference differential thing is added, it is also kind of a delta rule in this context. And eta is called learning factor. And this kind of rule we have seen earlier also, when a learner updates the learned parameters, the updation rules follow this kind of thing, like present value plus fraction of a differential value, right? So you can see that, and there are different ways. Delta rules, no, there are some variations. It is not the same. Like, but I'm talking about the structure. Structure is like this. But actually, you can understand that it is nothing but we are expressing that weighted average of between the present running average and the reward what you obtained. So if eta is half, it is simply the weighted average or average of instantaneous average, I should say. It is simply the, no, it is not simply integer. So eta is 1 by 1, because t into qta, t by t plus 1. So 1 by t plus 1, eta is 1 by t plus 1. Then it would be instantaneous average. And eta is decreasing with time. So eta is 1 by t plus 1. You can see that it would be the instantaneous average. Right. So note it down that thing also. Okay. Sorry, I have to proceed. So once again, now once you have once you have learned running averages, after some time, because this is converging, eta is decreasing with time. So after some time, you will find that not much of updates are there. So it has stabilized. You have learned the table. You have learned the table of this expected average for all actions. Then once again it remains the same. So you choose that action which will give you the maximum expected average, and that is how you are maximizing the return, expected return. Now I talked about just a very simple environment where you have a single state, and of course k actions. It has both deterministic and non-deterministic flavor. But the state environment was very simple in the sense that it was a single state. It has a single state. Naturally, in a complex environment, you have too many states. You consider the chessboard example itself. So there are so many possible configurations of states are possible. Like if you have, I don't want to put it right now instantaneously, but you can compute it, right? There are number of pieces, and also there are similar number of pieces. There are so many places, 64 places, and what kind of number of states are possible given the constants of the moves of different pieces. Okay, so it is a very large number. So multiple states of the environment, that is what in a complex environment. And in this case, naturally, as I started with, that action may affect the next step. So in a single state, you do not have this issue. But no, here action not only brings a reward, but also it changes the state. And this could be also non-deterministic. So everything could be non-deterministic. Change of state, getting a reward, this could be non-deterministic. So the agents, on the other hand, it's capable of sensing the state of the environment and also receiving a reward, negative reward. So this is how the model, in this case, learning, I should say the environment, the learning system, or the system, agent environment interacting system, it can model in this way that agent can sense the state. So after every action, there are two things. One thing is that what is the state transition taking place and whether there is any reward, and what is the reward. These are the two things you will get. And as I was mentioning, that this could be non-deterministic, which means now you have a probability distribution of reward, not only for the action, given action, but also the state on which this action is taking place. So so these two factors would be there. So you have to learn something like similar to running averages of value, expected return, or expected return, similar thing. So we will consider, just term them as value. So what is the value of taking action AJ in state SI? So you have to learn that, and you have to learn so many such. Now it is number of state multiplied by number of actions, right? So many parameters you have to learn. Okay. Also, the rewards may be delayed, that you should consider, but it may be delayed, but there is a need for immediate estimation of prospective reward, because no, you are exploring, and you need to consider that which actions are to be taken. So in which directions, what should be your preferred directions of your sequence of actions. So that's why there is a need for that. Otherwise, your options could be exponentials. So you would like to make it efficient. So that's why you need an immediate estimation, and that should be as accurate as possible, as you understand. So this process, this learning process, can be modeled like a Markov decision process. So you know that in Markov decision process, you are considering that that you can see that from every state there is a state transitions. You are taking an action, you are going to the next state. So the dependencies of state, you are going to the next state. You may say that it is the first order model, it may be the second order model, whatever. It is on the past states only the past states. So that is why this process is is there, and there would be, so all these two things, like it will require that I'm sorry, there's an error here. It should be state transition. Okay, this should be ST plus 1. This should be ST plus 1. So you are receiving a reward given at a state and action pair. Similarly, you are going to the next state, the environment moves to the next state. And this sequence of actions, also sometimes termed as episode, from start to the terminal state. Now, this is what you need to learn in this process, that if you are at certain state, which action you should take. Okay, which action you should take. This you need to learn. It's a kind of, we call it policy. So if the policy is there, that means there is certain, in this case, some kind of uniqueness is there. That means if you are in this state, take these actions, right? So the this mapping, that state to actions, for every state there would be only one action, right? That you are choosing. Now we can say that the value of a policy is that, as you see, that once you have defined a policy, then given a state, there would be always series of actions which are also well defined, because from every action you get a next state, and again you choose according to the policy what is the next action, and for every such state action there is certain return. Now these are all depending, all environments. It's not, it may be deterministic, it will be non-deterministic. As you see that there is a probability distribution, so there will be some return. So the value of a policy is that for a particular state, again, from any state, what is the value of policy from that state? Now, what is the return, expected return that you get, cumulative return you get? Okay, expected cumulative return for a certain, say, finite window, say till t steps, capital T steps. So we call it finite horizon. Or also you can say this may be infinite also. So we'll see that, of course, convergence is an issue if we consider infinite, and we'll see that how it is also taken care of. There is a concept of discounted return. We'll come to that. But this is how the value of a policy is estimated for a particular state. So given a state, if I specify the probability distributions, so as you can see that there would be certain probability distributions of reward or this value, if I say this is the value, this particular variable, which is basically expectation of all those things. As you know that this could be simply sum of all these expectations. So the objective here is now, as you can see that for performing this task, what you are learning a policy actually. You are learning a policy, which means there is a policy is a mapping of state to actions. So state action pairs. So given a state, what action you should take. So that is what is policy. So this could be in a framework where you are already given this to probability distribution. Sometimes these are also to be learned. I mean, it may not be given to you, but suppose it is given to you, and which we call actually the model of the environment, model of this particular system, agent environment interaction system. So if I specify these two, it is sufficient. Then, as you know that following these probability distributions, given any state, you can have a probability distribution of the value as we defined. Of course, policy has to be there. So given any state, you can have probability distribution of value. Again, for a given any state and action, you have a probability distribution of value, which means for all possible actions given a state, you have some probability distribution of value, expectation. So finally, you are considering expectation. It is not the distribution that you are bothering here. You are very much bothered about. Of course, distribution is there is an underlying distributions, but what is your objective is to choose that action which will maximize that expected return. So this you have to learn. So value of a policy, as I mentioned, this is the value of a policy, and discounted value with infinite horizon is expressed in this fashion. You can see that every future rewards are discounted by a factor gamma. Every time it is multiplied by a factor gamma. Every future. So finally, after some times, because the gamma value, it's a fraction, it's within 0 to 1. So after some time, this is very negligible, and this value will converge. So optimal policy would be that that particular for that particular policy for a particular state, which is maximizing this rate, So this is what, given a state, what is the optimum policy? So policy is basically state dependent, as you can see. As an alternative also, you can learn this factor. So you can see that optimal policy here, when you are doing reinforcement learning, it is also state dependent optimal policy, right? State dependent policy, depending upon from which state you are starting, there is certain policy you have to choose. And if it is optimal path, that there are theorems that all these state transitions, making that you will have the same policy. So there are interesting theorems and proofs which should be there. I did not go through them, but you can understand that moment you take a action, you are going to the next state. Now it should be the same optimal policy for that state transitions also. So policy remains same given the starting state. So within that path, since all the states are there, so there is a uniqueness of the policy also. If all the states are visited, only problem is that if all the states are exhausted in that path, otherwise it is a question of question of the reachability. So there could be also different optimal policies for different states, and there could be certain finally, for certain set of states, optimal policy in the optimal path, whichever state is lying from a particular state, they will have the same optimal policy. So this can be extended. These are all extended from an understanding. So as an alternative, as we are saying that we are learning QSTHE value at state with action. For every state, you are choosing what is the action. Right? So in this case, we are assuming every state, from every state, there will be a single path on which optimal path on which you can reach all of the goal. So this is a this is how this is expressed. It is simplified in this way. You can see that from this expression, this QSTAT is, I'm writing the same thing. Instead of writing the value V function, I will be also considering this. It is the same expression. Now, this part once again can be written as V pi ST plus 1, right? So that is the thing. So this could be considered as this, and then the action which is maximizing this value, that action should be now that is different, but it is max out of all actions. What is the maximum? And that is the policy. But choosing an action given the state, the argmax should also give you the sorry, that is the value. This is the value, and policy in the policy wise, the action which is giving this maximum, that should be stored for ST. Okay, so this is the same thing what is expressed here. So I think we're continuing how we are learning this option. So either you can express in the terms of value with single argument ST, or even you can consider state action pair, and you can choose it, and then you are choosing the action which has the maximum value, or you are choosing the action which is maximizing this particular in the Q form, in the Q function also, which is state action Q. Both are equivalent. Both are equivalent because you can see that these are equivalently expressed in this expression. Okay. You should note that Q contains the Q function contains more number of parameters because it is storing the value of state actions. In fact, you need to compute it to compute the value functions for a particular state, because you have to consider all possible actions. You check this particular equivalence. Say value is computed from the Q functions itself, where the Q function expresses values for state action pairs at any particular time instance. So out of all possible actions, what is the maximum value that is associated with the value of that state? And that is how you are expressing them. So if I give you the probability distributions, these computations are, through this kind of dynamic programming approach, you can compute all these things and you can determine a policy. Okay. So this is called model-based learning. So where in the models are known to you, model means this probability distributions are known to you, and we should directly solve for the optimal value function and policy. Okay, so we are basically computing the maximum value that is possible at a state S, when you reach a state S, what is the maximum expected value? So this can be computed. This can be computed in this fashion. And as you know that these are all connected with other states. So it has to be iterative also. It has to be iterative, right? We'll see that through iterations you are converging. So you start with any arbitrary values, then you perform these things. Now, the reward, you are getting reward, of course, through explorations. So this part, this reward you are getting through explorations, the state transitions, this is expectation. So if the probability distribution is also given, you can get it. Like if probability is given, then you are getting. So how actually during explorations you can do it, we'll come to that later part. But right now, theoretically, if this probability distribution is given, so you can compute the expectation, right? You can compute expectation. You can compute this expectation at a particular stage. You can also compute the corresponding, the values and this transition. So naturally, these are to be iterated. These are to be iterated for a convergence. So we'll see. So that iteration is required. Otherwise, this can be computed. And if I consider the policy, so once you have this value for each state, because these are associated with actions. So what action is giving you this maximum value? That action you store for that state, and that is what is the policy, and that is the optimal policy that you are learning. So there are two approaches. One is value iteration algorithm. As I was telling you, you iterate the values, and finally at the end you collect all those actions. Or you should remember the actions. Otherwise, at the end, how to do it? You remember the actions, and you get the policy. Whereas in policy iteration algorithm, so you start with a policy, arbitrary policy, then you perform all these things, and while doing these things, you update the policy. So in the value cases, value iterations, you are looking at the convergence of value sets for each state. In the policy iteration, you are looking at the convergence of policy, where the values, intermediate values are changing. So just, I should say almost equivalent approaches, but flavor would be a bit different. Okay. So this is the value iteration algorithm. You can see here that you are initializing the value to arbitrary values, as I mentioned, and then you perform these computations of value. So we are doing these computations using the Q functions. That means first we are computing the maximum value that is possible for a state action pair. Then given a state, maximum value is possible over all actions, right? And then you are also storing immediately you are storing the state action, but what you are considering how the values are converging. Whereas in the policy iteration algorithm, you are updating the policy directly from intermediate values. And then you are looking at the convergence of the policy. So initialize this policy to arbitrary values, right? Instead of initializing values, and then you compute the values. So you compute the values using that policies, and then you improve the policy at each stage. In fact, while computing the values itself, your policy gets updated. You know that you are storing the maximum action there itself, right? And then improve the policy. That means you store the action and you go on doing these things till you find that these are converging. I think today let me stop here. Again, on Friday, we'll have the next part. So far, as we see that we have learned this kind of what is the difference from the supervised learning, what is the difference in paradigm of reinforcement learning, what are the differences there, and there particularly, if I give you a model in an environment where there are multiple states and an agent which can take multiple actions and get rewards, also the get changes in the state, and objective is to reach certain goal state, but that is expressed in terms of getting rewards, so maximizing the rewards. So if the model is given, then we can see that we can compute, finally, we can compute the expected values or expected returns at every state of the environment for that agent. And the immediate action that you have taken at that state, that is noted, and that is what is the policy. So in a non-deterministic sense, if the deterministic sense, you know that no, you are just finding out observing what is the reward you are getting after every step. That is the deterministic consequences. But in the non-deterministic cases, it is not the same reward. Rewards will vary with certain probability distribution. Even the state transitions, it is not deterministic. That means from a state there could be different, it can move to different states for the same action. So there you should consider the expectation of the reward for that action, and then you are computing the value of prospective reward. What is the series of actions? What is the estimation of the reward, cumulative rewards from a series of actions, right? So that is the value part for that state. And the action by taking which you are maximizing that prospective value, that action needs to be stored. That is the policy part. So finally, you are learning policy. Finally, you are learning policy, which you can use in future for an agent given a state, which action to be taken to maximize your reward. Okay, so with this, let me stop today. And if you have any questions, I'll be very happy to respond. Okay, so have a nice Diwali, and we will meet again day after tomorrow. So tomorrow is a holiday. Enjoy your Diwali. Thank you very much. Bye.